Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and in the last couple of lectures of ECE3400 analog electronics, we looked at good old-fashioned diodes. Here we're going to specifically focus on Zener diodes, particularly their use as voltage references and voltage regulators. So how does a Zener diode act? Well, it basically acts like the junction diodes we've been talking about. The main difference between a Zener diode and a standard diode is that a Zener diode is designed to have a guaranteed Zener voltage and will let you operate it in that Zener region without blowing up. So these special Zener diodes are indicated by a special symbol on this line. I like to imagine that the standard line representing the cathode of a diode is morphed to look a little more like a Z. Sort of. And if you forward bias the Zener diode, it acts just like a regular diode. And there are some circuits that use Zener diodes that rely on this kind of characteristic in addition to its Zener characteristic. But arguably the most standard way to use a Zener diode just operates it in this reverse bias mode. And since we're operating it in that reverse bias mode, it's convenient to define a Zener current IZ that's just the opposite direction of ID. So that way IZ can be a positive number, which is more convenient to work with. So let's talk about how you might use a Zener diode to create a primitive voltage regulator. Now, as I'll discuss later, this is not actually a very good voltage regulator. To make a good voltage regulator, you need to have some additional transistors and this, that, and the other. You basically need some kind of active electronics. But we can learn a lot from this particular example. So let's add a voltage source and a resistor. And this voltage source may be what's provided to our circuit from a battery or from some sort of AC to DC converter like the wall warts that you plug into your wall socket. And we want to use the structure here to create a voltage that we can use to power some load. And I'm going to represent the load for now as a current sink IL. Now, in most practical applications, the load current of the circuit you're building isn't constant. So let's suppose we can bound it by IL min and IL max. Assuming we've selected everything here so that we are operating in this Zener breakdown region here, we can suppose that a voltage VZ is induced at this node, where the minus here from having flipped around the diode symbol cancels the minus over here. Okay, so what's the current I1 flowing through this resistor? Well, I can take the voltage difference across the resistor, which is V1 minus Vc, and just divide it by R1 according to Ohm's law. But I can also write a Kirchhoff current law equation. The current I1 flowing into this node is equal to the sum of the currents flowing out of the node, IZ and IL. So if I divide both sides of the equation by IZ plus IL and multiply both sides of the equation by R1, I can write R1 equals V1 minus Vz over IZ plus IL. So to choose R1, we need to make some assumptions. Let's choose IL to be the maximum that the load current is going to be. That's going to define the most current that's going to need to flow through R1 in order to supply the rest of our circuit. Now, what about IZ? Well, if you look at most data sheets for Zener diodes, the Zener voltage is usually expressed in terms of an associated test current, and that's the current that they tested the diode at that gives you that Zener voltage. So let's plug that in, and that defines a certain amount of current we want flowing through the Zener in order to try to get the correct Zener voltage. For instance, if you check out this Zener diode datasheet, it lists a whole bunch of diodes, and it will list its nominal Zener voltages, say 3.3 volts, or 3.6 volts, or 3.9 volts, depending on the particular diode type. And it'll say it's measured at a certain test current. Here it's IZT1, so here it's indicating 76 or 69 or 64 milliamps. So we would want to design our circuit to have that amount of current flowing through the diode. Now, once you've picked R1, you need to make sure that you don't blow up R1. So you can check the amount of power that's dissipated in that resistor and choose your resistor accordingly. And here I'm using the voltage squared over resistance form of the expression. I'm using this form of the expression because it seems to be the most convenient in this context. All right, Now, we also need to make sure that we don't blow up the diode. Okay, so what is IZ? Well, that's going to be I1, the current flowing through the resistor, which by Ohm's law is V1 minus VZ over R1. That's the thing we found before. But to get IZ, we also need to subtract IL. And which IL? Well, to check the worst case scenario, let's use the minimum current load, because the minimum load current will correspond to the maximum current through the diode. Now, all of this analysis is assuming that this VZ is really staying constant. It doesn't. A little bit later, I'll talk about how you might pull off a more detailed analysis, but actually, in most applications, it's probably not worth the effort. In the most extreme case, you might have a situation where the load might become disconnected altogether, and then all of the current flowing through R1 flows through the diode, and the diode needs to be able to handle that. Now, sometimes loads might not be specified in terms of the current they draw directly. They might be specified as some sort of load resistance RL, in which case we might have a situation where we know there's a range that our load resistance is going to vary between. And here I can take the formulas that we've already computed and pretty easily tweak those, because the minimum current flowing through the load is going to correspond to the maximum resistance, and the maximum current is going to correspond to the minimum resistance. So all I need to do is to take these IL min and IL max quantities and plug them into the expressions on the right-hand side here, and that will give you formulas that look something like this. So nothing too terribly fancy. So that's how you could use a Zener diode as a voltage regulator, but I don't really recommend it. It's not really that great of a voltage regulator. One of them is that you are wasting a whole lot of power in this resistor, so it's not very energy efficient. The other thing is that we've really been assuming that this VZ is staying constant, which is basically assuming that this curve is a vertical line, but it really does have some slope to it. So if you think back to our small signal model on junction diodes, we defined a dynamic resistance RD. We could also define a dynamic resistance RZ over here on the Zener side of the graph, and then that dynamic resistance RZ is the reciprocal of the slope of the curve at this point. And you can use that information to do a more detailed analysis. You can build a model for the Zener diode that consists of a battery in series with a resistance RZ, and then redo all of this analysis, but make it more fancy. But in general, it's not worth bothering. If you want a voltage regulator, you should really buy a voltage regulator. Get a TL431 or some fancy low dropout regulator. You'll get something that you'll be happier with. Now, if you are curious about this RZ, you can usually find some guesses about that on the datasheet, and it will usually give a range at different values. For instance, at a test current IZT1 of, say, 76 milliamps for a 1N4728A, that dynamic resistance we called RZ. Let's see, here they call it ZZ. But anyway, it's just something like 10 ohms. So that tells you the curve is very steep at that point. But tested at another current IZT2, namely 1 milliamp, that rises to something like 400 ohms. So that's a much less steep part of the curve. So although Zener diodes don't make very good voltage regulators, they make great voltage references. So let's imagine that we want to set a voltage at a particular node in a circuit, but we don't need to draw current from it. We can address this case by setting this load resistance to infinity, in which case these formulas simplify because this term drops out and this term drops out, and we get a little something like this. So I want to emphasize the difference between voltage references and voltage regulators. Voltage references are like setting a constant in a computer program. It's a piece of information that you're using in the circuit, and in particular, you're using it on something that doesn't need a source or sink a lot of current. So maybe you have a signal that you want to compare to some particular voltage. So we might have our signal coming in up here, and then here's your comparator. So this is something like an op-amp being used in open loop mode. So the output here is going to rail all the way one direction or the other. It's basically giving a true or false output. Is this bigger than that? You could use a standard op amp for this, but it's usually more convenient to use something like an LM311 that's a dedicated comparator that's specialized to act as a good comparator, but your mileage may vary. But the important thing to note here is the reference does not need to sink or source a whole bunch of current. You're assuming that this VZ node is feeding something that has a high impedance input. And then you can choose R1 directly just by looking at what the test current is for that Zener voltage. Remember, a voltage regulator needs machinery in order to be able to source or sink however much current it needs to while still holding its output at the correct voltage that you want. So Zener references are often used inside voltage regulators. So here's the classic 78,000 series of voltage regulators. And you'll see there's a whole bunch of transistors doing this, that, and the other, but you'll also see that there's a couple of Zener diodes in here that are providing voltage references. As the folks at Adafruit like to say, that has been your moment of Zener. Now, if you're not taking this class for credit with me at Georgia Tech, you can check out now. But if you are one of my Georgia Tech students who is taking this for credit, I would like you to go to Canvas and click on Quizzes. And there you will find a quiz called Zener Video Quiz. This quiz formally just has one question, but there's really two questions I want you to answer in that particular quiz entry spot. I'm going to ask you about your favorite class and your least favorite class, not including any classes that I've taught. So, first, what is your favorite class and what aspect of that class did you like the most? 2, what is your least favorite class and what aspect of that class did you dislike the most? Again, don't include any classes I've taught in either question 1 or question 2. This is just out of my own curiosity because I spend a lot of time thinking about teaching and I like to get your perspective on these kinds of topics. I'll keep this information to myself.